Hi, my name is Shrey, and I'm the software lead for Michigan RoboSub, and I'm really excited to introduce our team and present our competition strategy for the 2022 International RoboSub competition. Michigan RoboSub is a student project team at the University of Michigan, and we're going into our second year of competing in the RoboSub competition. Our latest autonomous underwater vehicle, Erie, is the product of a year of learned technical and organizational experience. We faced a number of challenges having our first year as a team disrupted by the global pandemic, but after 2 years of hard work from all of our members, we came out stronger, smarter, and more determined than ever. Being a second-year RoboSub team, this upcoming 2022 competition will be the first time we present our submarine in person. As such, we chose to keep a limited but focused scope in terms of selecting competition tasks. Our goal was to do the most straightforward tasks, but to do so thoroughly and reliably. Our submarine from our first competition season, Huron, was a great start, but we made several changes when designing Erie in order to address the numerous problems that came up in the manufacturing process, the electrical component placement, and the software testing. For Erie, a big emphasis was placed on modularity. The mechanical design is such that once the complex hull was fabricated, the rest of the sub could be easily manufactured and assembled. The hull is open and spacious, allowing for easy electronics placement, and has an upward-facing window, allowing us to monitor indicator lights from dry land. Being a relatively new RoboSub team, a lot of our software team's time was dedicated to designing our perception, navigation, and control algorithms, and architecting a system which seamlessly integrates all of these complex components. We aim to accomplish 3 tasks at the 2022 competition: choose your side, make the grade, and cash or smash. We focused a lot of attention on completing the choose your side task. It is not only the qualifying task for this competition, but requires a synthesis of perception, task planning, and navigational algorithms, which captures the elements required for all the subsequent tasks. Our thinking was if we can successfully accomplish this task, then we can build our system architecture to complete more and more of these challenges. The gate's brightly colored side posts make it visually unique in the water, making it perfect for computer vision applications. We rely on a deep learning multi-class object detection model to identify all the images in the water. This multi-class approach means we can recognize multiple images at once, allowing us to more efficiently navigate the pool. Our machine learning algorithm detects the gate, then we calculate the relative angle the submarine has to turn to keep it in center view. As long as the submarine is facing within 15 degrees of the gate, it moves forward, approaching the center. As the submarine gets closer to the gate, the G-man and bootlegger images become visible. This is where our multi-class model comes in handy. As we're approaching the center of the gate, we're constantly looking for the G-man and bootlegger images. Once they're detected, the submarine switches from maneuvering towards the gate to maneuvering towards the bootlegger image. This process of first centering on the gate, then centering on the image, makes our system robust to visibility and water clarity issues. The submarine continues on this trajectory, moving towards the bootlegger image, until the image is no longer visible. At this point, we know that the submarine is about to cross the gate, so it switches to moving forward slowly while utilizing a bottom camera to look for the next task. After we cross the gate and complete the choose your side task, we use the path marker to orient the submarine towards the buoy and go for the make the grade task. To align towards the buoy, we use classical computer vision algorithms to detect the angle of the path marker and have the submarine turn towards that angle while looking for the buoy. Once the buoy is detected, the submarine follows a similar procedure as with the choose your side task. Our machine learning model handles the detection, then the relative angle is calculated, and the submarine approaches the buoy. An added difficulty in this task is determining when the sub has made contact with the buoy. We do this in 2 ways. First, we keep track of how much of the camera view the buoy takes up as we approach it. Once the buoy takes up about half the camera view, we know that collision is imminent. We then track irregularities in our attitude and heading reference system with the knowledge that when the buoy is hit, the submarine will be shaken, indicating that we have successfully completed this task. Last, we attempt the cash or smash task. This task was less of a focus for the team since the acoustic navigation required is very complex and less applicable to other tasks. We use 3 hydrophones mounted in a triangle shape and perform elaborate low-level filtering and signal processing. Using precise measurements of the hydrophone's locations, we can do some relatively simple geometry to determine the pinger's direction relative to the submarine. We then move towards this direction and surface when the signal is strongest. A hydrophone system is less reliable than our computer vision algorithms, but since there are no further tasks to attempt after cache or smash, there's only an upside in trying for this task. Our strategy as a team is to set up the right infrastructure in our mechanical, electrical, and software subteams and as an organization to succeed not only this year, but to excel in all future RoboSub competitions. Michigan RoboSub is all about striving for success and improving on our shortcomings. We're a young team with the right mindset, and we reach for the stars. Thanks so much for listening to our presentation, and go Blue!